US Physics Olympiad, year 2015, F equal MA. First round. This round consists of 25 problems. It was given 75 minutes for these problems. All solutions for all these problems you can find in the description below of this video. And please subscribe for the channel. In that case, you have chance to get all problems from American and other Olympiads. Problem 1. A 600 meter wide river flows directly through 4 meters per second. A small motor boat travels at 5 meters per second in still water and points in such a direction so that it will travel directly east relative to the land. What is the closest time it takes to cross the river? Solution. Here we can use vector diagram. Let's V be the vector of river flow, which is 4 meters per second. And let's V0 be the vector of velocity, which is 5 meters per second. This vector V is going to south, and V0 is going such way that total vector going to east. So we can sketch the diagram. So from this diagram we can see that to construct vector which is going to the east, we have to create a right triangle from which we can find what is the speed. That will be 3 meters per second. So finally we can find what is total time to travel for this boat. That will be distance of V prime, which is 200 seconds, which is answer D. Problem number 2. A car travels directly north on a straight highway at a constant speed of 80 kilometers per hour for a distance of 25 kilometers. The car then continues directly north at a constant speed of 50 kilometers per hour for a distance of 75 more kilometers. The average speed of the car for the entire journey is closest to solution. Here we have to use definition for average speed. That will be total distance divided by total time. And the total distance equal distance d1 plus distance d2, which is 25 plus 75 kilometers, divided by total time, which is t1 plus t2, and each time equal to distance divided by speed, which is this expression. And finally, when we put numbers, we will get 55.2 kilometers per hour. That's result A. Problem number 3. The force of friction on an airplane in level flight is given by F friction equal kV square, where K is some constant and V is the speed of the airplane. When the power output from the engine is P0, the plane is able to fly at the speed V0. If the power output of the engines is increased by 100% to 2P0, the airplane will be able to fly at a new speed given by solution. Here we can write the expression for power. Formula for power. For flying with a constant speed, power must be equal to force multiplied by speed, which is kV cube. It means that P0 equal kV0 cube. If we increase power twice, we can use this formula to find what is a new speed. That will be cubic root from 2 V0, which is approximately 1.26 V0. That's the answer B. Problem number 4. A 2 kg box is originally at rest on a horizontal surface where the coefficient of static friction between the box and the surface is μs, and the coefficient of the kinetic friction between the box and the surface is μk, equal 0.90 μs. An external horizontal force of magnitude P is then applied to the box. Which of the following is a graph of the acceleration of the box A versus the external force P? Solution. The block will not move till force will not exceed some amount, which is given by this formula. And when a force reaches this amount, this force will discontinue and will jump according to formula acceleration equal this amount. It means that acceleration will have a jump in this point. So it means that we have originally D and E not correct because of this one. B is not correct because acceleration not proportional to force, it's shifted down. And it's not C because it has to discontinue in this point. So we have only A is a correct answer. Problem number 5. A 470 gram lead ball is launched at a 60 degrees angle above the horizontal with an initial speed of 100 meters per second directly toward the target on a vertical cliff wall that is 150 meters away as shown in the figure. Ignoring air friction, by what distance does the lead ball miss the target when it hits the cliff wall? Solution. This problem better to solve in the frame of reference which start to fall down with the acceleration g in the moment of shot. In this frame, target will not move and the ball will move directly to the target with a speed 100 meters, and we can count at what time it will reach this target. That will be distance over speed, which is 1.5 seconds. But the target actually is not moving. So we have to find what distance will travel our frame of reference with a movable target. That will be 1/2 gt square. This is the distance which ball miss the target. That's about 11 meters, which is answer E. Problem number 6. 3 trolley carts are free to move on a one-dimensional frictionless horizontal track. Cart A has a mass of 1.9 kilograms and an initial speed of 1.7 meters per second to the right. Cart B has a mass of 1.1 kilograms and an initial speed of 2.5 meters per second to the left. Cart C has a mass of 1.3 kilograms and is originally at rest. Collisions between carts A and B are perfectly elastic. Collisions between cart B and C are perfectly inelastic. What is the velocity of the center of mass of the system of the 3 carts after the last collision? Solution. Because this system does not affected by any external forces, there are no friction, the velocity of center of mass it's not changing. It's not affected by any amount of collisions. So we can count just velocity of center of mass before all collisions. That will be this formula, which is a total impulse multiplied by total mass, which is after all calculations, that will be about 0.11 meters per second, which is answer A. Problems 7 and 8. The following information applies to questions 7 and 8. Carts A, B, and C are on a long horizontal frictionless track. The masses of the carts are m, 3m, and 9m. Originally, cart B is at rest at the 1 meter mark, and cart C is at rest on the 2 meters mark. Cart A is originally at 0 meter mark, moving toward the cart B at a speed of v0. Question 7. Assuming that all collisions are completely inelastic, what is the final speed of cart C? Solution. Because all collisions are inelastic, finally all these three carts will move together, and the cart C will move with the velocity of center of mass, total system. And this velocity we can find from this formula. Velocity of the third cart will be total momentum mv0 divided by total mass, which is 13m. And the answer is v0 over 13, which is A. Question 8. Assuming that all collisions are completely elastic, what is the final speed of cart C? Solution. Here we can use the standard result for in case when one cart is moving and the other is not moving is this one. As we can see from formulas, after first collision, the first car will move back and the second car will move forward with the speed v0 over 2. Same thing will happen during the second collision. Second car will move back and the third car will move forward with the speed v0 over 4. That's the solution, B, correct one. Problems 9 and 10. The following information applies to questions 9 and 10. A 0.65 kilogram ball moving at 5 meters per second collide with a 0.75 kilogram ball that is originally at rest. After the collision, the 0.75 kilogram ball moves off with a speed of 4 meters per second, and the 0.65 kilogram ball moves off at a right angle to the final direction of motion of the 0.75 kilogram ball. Question 9. What is the final speed of the 0.65 kilogram ball? Solution. Here we can draw a diagram, and from this diagram that will be easy to find the answer for the question. In the case of this collision, we have momentum conservation. It means that initial momentum P of the first ball, it was split by P1 and P2 by right angle. So from here we can write equations. In vector form we have P equal P1 plus P2, but because this angle is right, we can write another equation. We have P square equal P1 square plus P2 square. And now we can insert momentums. We have this equation from which we can find what is the speed of the first ball v1 after collision, equal this expression, or after put numbers we have 192 meters per second, which is answer A. Question 10. Let the change in total kinetic energy in this collision be defined by delta K equal Kf minus Ki, where Kf is the total final kinetic energy and the Ki is the total initial kinetic energy. Which of the following is true? Solution. First of all, without calculations, we can tell that this collision is not absolutely elastic, because only in case of two equal masses we can have the angle between final momentums could be 90 degrees, but our balls have different masses, so it's not perfectly elastic collision. It means that the final kinetic energy less than initial kinetic energy. And we can tell that delta K must be negative and less than Ki in value. And from this point we can check our answers. So first answer, delta K equal this one. It's not correct, because delta K is negative and the right part is positive. Same thing with B. We have Kf is positive and delta K is negative. C is not correct because delta K is negative. D is not correct, delta K is negative. And E is correct because delta K is negative, and by value that's less than Ki. So E is correct answer. Problem number 11. A sphere floats in water with 2/3 of the volume of the sphere submerged. The sphere is removed and placed in oil that has 3/4 the density of water. If it floats in the oil, what fraction of the sphere would be submerged in the oil? Solution. Because 2/3 of sphere submerged in the water, we can write equation. Volume of a sphere multiplied by rho sphere equal 2/3 volume of a sphere multiplied by rho water. From here we can find that rho sphere equal 2/3 rho water. And also we know that we have rho water equal 4/3 rho oil. If we put this to this one, we will get that rho sphere equal 8/9 rho oil. It means that 8/9 of sphere will be submerged in oil, which is answer C. Problems 12 and 13. The following information applies to questions 12 and 13. A pendulum consists of a small bob of mass m attached to a fixed point by a string of length L. The pendulum bob swings down from rest from an initial angle theta max less than 90 degrees. Question 12. Which of the following statements about the pendulum bob's acceleration is true? Solution. First, let's draw the picture. As we can see from picture, acceleration of this pendulum has two components. One is tangential and the other is centripetal. And we can write expressions for these accelerations. For tangential, that will be at equal g sine theta, and for centripetal, that will be v square over L. V square we can find from energy conservation. So that's the expression for v square. And when we put v square in this formula for centripetal acceleration, we can get a result for centripetal acceleration. Now let's estimate all sentences here. A. The magnitude of the acceleration is constant for the motion. As we can see, it's not constant. It's decreasing for tangential and it's increasing for centripetal. And if we count what is total, we have to do square root from at square plus ac square, which is not constant either. B. The magnitude of the acceleration at the lowest point is g, the acceleration of free fall. In lowest point we have tangential equal 0 and the centripetal equal 2g multiplied by cosine theta, which is 1 minus cosine theta maximum. So that's not g. C. The magnitude of the acceleration is 0 at some point of the pendulum's swing. As we can see, it's not 0. Tangential has a 0 in the lowest point and centripetal 0 in the highest point. But both they don't have 0 magnitude in any point. D. The acceleration is always directed toward the center of the circle, which is not true. We have tangential acceleration which is not going to the center. E. The acceleration at the bottom of the swing is pointing vertically upward. That's true. Tangential equals 0 and the centripetal is going vertically. So that's correct answer. Question 13. Consider the pendulum bob when it is at angle theta equal 1/2 theta maximum on the way up, moving toward theta maximum. What is the direction of the acceleration vector? Solution. Let's compare this to our previous result. We had a result for tangential acceleration as g sine theta, which is always going down and left, and the centripetal acceleration, which is going to the center of rotation. If you look at this picture, we always have acceleration pointing to the left and to up compared to point of rotation. And only for diagram D we have this result. Other pictures, they are not consistent with this result. So correct answer is D. Problems 14 and 15. The following information applies to questions 14 and 15. A 3 meters long massless rod is free to rotate horizontally about its center. Two 5 kg point objects are originally located at the ends of the rod. They are free to slide on the frictionless rod and are kept from flying off the rod by an inflexible massless rope that connects the two objects. Originally, the system is rotating at 4 radians per second. Assume the system is completely frictionless and ignore any concerns about the instability of the system. Question number 14. Calculate the original tension in the rope. Solution. Tension we can calculate using formula mass multiplied by centripetal acceleration, which is radius multiplied by omega square. So this is the answer. Tension equal mr omega square, which is 120 newtons. That's the answer C. Question number 15. The rope is slowly tightened by a small massless motor attached to one of the objects. It is done in such a way as to pull the two objects closer to the center of the rotating rod. How much work is done by the motor in pulling the two objects from the ends of the rod until they are each 0.5 meters from the center of rotation? Solution. Here we can represent kinetic energy using formula K equal 1/2 I omega square, or this way, 1/2 1 over I multiplied by L square, where L is angular momentum, which is in our case is conserved. So now we can count what is the work done by motor. That's equal to kinetic energy difference between final and the initial position, which is this one. Now let's count what is L, I2 and I1. Angular momentum we can count from initial position, which is in the final position the same. So that's equal to masses multiplied by R1 square multiplied by omega, which is 90 in SI unit system. I2 in second position equal to M multiplied by R2 square, which is 5 over 2. I1 equal to M multiplied by R1 square, which is 45 over 2. And finally we can put these numbers to this expression and get the answer. The work will be equal to 1440 joules, which is answer D. Problem number 16. Shown below is a graph of potential energy as a function of position for a 0.5 kilogram object. Which of the following statements is not true in the range of from 0 to 6 centimeters? Solution. Let's check all statements. A. The object could be at equilibrium at either x equal 1 centimeter or 3 centimeters. Equilibrium position has a definition for force equal 0. So in a graph it means that slope in this point must be equal 0, which is in 0.1 centimeter and 0.3 centimeters. In point 1 we have unstable equilibrium, and in point 3 we have stable equilibrium. So A is not good. B. The minimum possible total energy for this object in the range is negative 10 joules. That's true. In point 3 we can have object with 0 kinetic energy and negative 10 potential energy, which is total negative 10 joules. That's true. C. The magnitude of the force on the object at 4 centimeters is approximately 1000 newtons. Let's check. Here we have slope is 10 divided by 1 centimeter, which is 0.01 meter, and the slope is 1000, which is true. So it means that C is not correct. D. If the total energy of the particle is 0 joules, then the object will have a maximum kinetic energy of 10 joules. That's true. If we have total energy in 0 level, we have a maximum possible kinetic energy in point 3, where we have a minimum potential energy, negative 10. So that will be for kinetic energy 10 joules, which is correct. means that D is not good. E. The magnitude of the acceleration of the object at x equal 2 centimeters is approximately 4 centimeters per second square. Let's count it. We can count what is the acceleration using this formula. Acceleration equal F over m, which is negative delta E over delta x multiplied by 1 over m. In 0.2 centimeters, we can count what is the slope. If we measure it from 1.5 to 2.5, that's approximately 20, and distance is 1 centimeters, which is 0.01 meter, and we multiply it by 1 over 0.5 kilogram, which is 4,000 meters per second square, which is not 4 centimeters per second square. It means that this is not correct, and this is the answer for our question E. Problem number 17. A flywheel can rotate in order to store kinetic energy. The flywheel is a uniform disc made of material with density ρ and tensile strength sigma, measured in pascals, the radius r and the thickness h. The flywheel is rotating at the maximum possible angular velocity so that it does not break. Which of the following expressions correctly gives the maximum kinetic energy per kilogram that can be stored in the flywheel? Assume that alpha is a dimensionless constant. Solution. In this problem we have to use dimensional analysis, and for that we have to find the exponents for this expression, which should give us energy per mass units. So it means that we have to insert, instead of these variables, dimensions. Their dimensions. Dimension for ρ it's mass over L cube. Dimension for tensile strength, that's pressure, that's mass per length per time square. And for R and H, dimension is L. And the result must be L square over T square. So first of all, we see that we cannot resolve this problem straight, because R and H have the same dimension and there are no way to distinguish them. But it's obviously, if we increase thickness twice, we increase mass twice, and we increase energy twice. So it means that D must be equal 0. And the other equations looks like this. For unit mass, we have A plus B equals 0. For unit length, we have negative 3A minus B plus C equal 2. For unit time, we have negative B equal negative 2. So it means that B equal 1, A equal negative 1, and C equal 0. That's the answer E, correct one. Problem number 18. Shown below are 3 graphs of the same data. Which is the correct functional relationship between the data points? Assume A and B are constants. Solution. Because middle graph is a straight line, we can correctly write logarithm y equal ax plus b. Or we can rewrite it in form of y equal a multiplied by exponent and power bx. So that's a solution D. Problems number 19 and 20. The following information applies to questions 19 and 20. A U-tube manometer consists of a uniform diameter cylindrical tube that is bent into U shape. It is originally filled with water that has a density ρW. The total length of the column of water is L. Ignore surface tension and viscosity. Question 19. The water is displaced slightly so that one side moves up a distance x and the other side lowers a distance x. Find the frequency of the oscillation. Solution. Here we have to write equation for motion of this part of water inside the tube. This is the regular Newton equation. M is the mass of this water in a U tube, and F is a restoring force. Mass equal density of water multiplied by volume, which is cross-sectional area A multiplied by length L. Restoring force F equal the weight of a column which have height difference 2x, and the volume for this column is 2xa multiplied by rho, that's a mass, and multiplied by g, extra weight. So now equalizing these two expressions, we have this view, and after proper subtractions we have acceleration equal minus 2g over Lx, which has a regular canonical view for harmonic motion. Here we have x is displacement and a is acceleration. So from here we can find that frequency will be 1 over 2 pi square root from 2g over L. That's the answer A. Question number 20. Oil with a density half that of water is added to one side of the tube until the total length of oil is equal to the total length of water. Determine the equilibrium height difference between the two sides. Solution. Let's draw the picture. Yellow, that's a column of oil, and blue is a column of water. We have a height difference x, and the length of each column is L. Now we can write equation for pressure equivalence in a level which is dividing oil and water from left side, and the same level on the right side. So we have this equation for pressure from right side and from left side, and because raw oil is twice less than raw water, we have solution x equal L over 2, which is answer B. Problem number 21. An object launched vertically upward from the ground with a speed 50 meters per second, bounces off of the ground on the return trip with the coefficient of restitution given by CR equal 0.9, meaning that immediately after a bounce the upward speed is 90% of the previous downward speed. The ball continues to bounce like this. What is the total amount of time between when the ball is launched and when it finally comes to a rest? Assume the collision time is 0. The bounce is instantaneous. Treat the problem as ideally classical and ignore any quantum effects that might happen for very small bounces. Solution. First, we can write expression for time of flight. Each time after bounce, time flight is equal to 2v over g, where n is number of collisions. And to find what is the total time, we need to summarize all of this time tn. But each time when we have bouncing, we have Vn equal Cr multiplied by previous speed. And that's equal to Cr power n multiplied by V0, initial speed 50 meters per second. Now we can put this to expression and find that Tn equal 2V0 over G multiplied by Cr power n. And total time will be this sum from n equals 0 to infinity, and after all we have sum of geometric progression which has this form, and the final result is 100 seconds. Problem number 22. A solid ball is released from rest down inclines of various inclination angles theta, but through a fixed vertical height h. The coefficient of static and kinetic friction are both equal to mu. Which of the following graphs best represents the total kinetic energy of the ball at the bottom of the incline as a function of the angle of the incline? Solution. Here we can find that initially when angles are very small, less than critical, it means that tangent theta less than coefficient of friction, our ball is moving without sliding and we are not losing kinetic energy. It means that only C, D and E could be solutions for this case, not A and B, because they start to lose kinetic energy from the beginning angles. Later, when angle increasing almost to 90 degrees, we have very small friction and we are not losing energy at all when angle going to 90 degrees. It means that only C and D could be possible solutions, not E. And finally, we can tell that this graph must have a continuous function, because initially when we just reach the critical angle tangent theta equal mu, we are losing just a slight energy, and if we increase this angle, this loss of energy will increase, and after when we reach the minimum, a loss of energy start to decrease and finally is going to zero. It means that here we are not losing energy. But on graph D, we start to lose a lot of energy just after critical angle, which is not true. So most possible diagram is C. I would say this diagram is not formally good enough, because this behavior of function, it has no gap for the first derivative of this function. So it means that this graph represents not very correct answer, but still it's a best choice, C. Problem number 23. A 2 kilogram object falls from rest, a distance 5 meters, onto a 6 kilogram object that is supported by a vertical massless spring with a spring constant K equals 72 newtons per meter. The two objects stick together after the collision, which results in the mass spring system oscillating. What is the maximum magnitude of the displacement of the 6 kilogram object from its original location before it is struck by the falling object? Solution. Here we have several steps to solve this problem. First step, we have to find what is the speed of the first object of 2 kg when it reached the second object. Here we use energy conservation. To find this speed, V0, we use this formula, V0 square equal 2gh or 100, and the speed equal 10 meters per second. Second step is to find what is the common speed of both objects when they stick together. Here we use momentum conservation. From momentum conservation we can find that the common speed of these two objects, v1 equal m1 over m1 plus m2 multiplied by v0, which is 2.5 meters per second. Next step, we can use energy conservation. So we have kinetic energy of two objects, which we can count, and it's turning to potential energy of these objects in the lowest point when they stop. So their kinetic energy equal 1/2 m1 plus m2 multiplied by v1 square, which is 25 joules. Last step, we can use energy conservation. For that we have to find the initial compression for spring, which will give us initial potential energy of spring. X initial equal m2g over k. And now we can write the energy conservation. We have a final potential energy for spring equal 1/2 kx plus xi square. That's equal to potential energy of these two masses, gravitational potential energy, plus initial potential energy of spring, plus kinetic energy. After all, it will give us this quadratic equation. When we put numbers, we have this quadratic equation. We have two roots. One is positive, which represent the lowest position, and the negative represent the highest position. And by magnitude, lowest position will be greater than highest position. So this is why we have for answer positive root, and that's equal about 1.15, which is B answer. Problem number 24. The speed of a transverse wave on a long cylindrical steel string is given by formula V equals square root from T over M over L, where T is the tension of the string, M is the mass, and the L is the length of the string. Ignore any string stiffness and assume that it does not stretch when tightened. Consider two steel strings of the same length, the first with the radius R1 and the second thicker string with the radius R2 equal 4R1. Each string is tightened to the maximum possible tension without breaking. What is the ratio F1 over F2 of the fundamental frequencies of vibration on the two strings? Solution. When we increase radius 4 times, we increase cross-sectional area 16 times. It means that we can increase maximum tension 16 times. But from other hand, we increase mass 16 times, so we increase linear density 16 times. So it means that numerator and denominator we increase 16 times. It means that speed will not change for transverse wave. And we have speed equal fundamental frequency multiplied by wavelength, and because strings have the same length, lambda will be the same. So it means that the answer is 1. Problem number 25. Two identical cards A and B, each with mass m, are connected via a spring with a spring constant K. Two additional springs, identical to the first, connect the cards to two fixed points. The cards are free to oscillate under the effect of the springs in one-dimensional frictionless motion. Under suitable initial conditions, the two cards will oscillate in a phase according to this equation, where XA and XB are the locations of cards A and B relative to their respective equilibrium positions. Under other suitable initial conditions, the two cards will oscillate exactly out of phase according to this equation. Determine the ratio omega-2 over omega-1. Solution. When we have oscillation in a phase, it means that distance between card A and card B is constant. It means that spring between them is not acting with a variable force, and only left spring acting on card A and the right spring acting on card B. So it means that they looks like they oscillate independently. It means that on card A we have only force from spring with constant K, and omega-1 equal square root from K over M, and the same omega-1 is for card B, so that will be common omega for both cards. In second case, when they oscillate in out of phase, it means that we can take a middle point of this figure, and this middle point is not moving. So it means that card A affected by one spring with a constant K and other half spring with a constant 2K. They are connected in parallel, so total constant for both springs will be 3K. In that case, omega-2 equal root from 3K over M. It means that omega-2 over omega-1 equal root 3, which is answer A.